We're going to talk about chemical reactions. In a chemical reaction, we have one or more substances that are being destroyed and converted into one or more different new substances. A chemical reaction is a chemical change. So remember that in a chemical reaction or a chemical change, we have atoms being rearranged, repartnering to make new molecules, but we don't have any atoms being created or destroyed. Not in a chemical reaction. Can atoms be destroyed? Not in a chemical reaction. Well, how about in a nuclear reaction? Yeah, they can be destroyed in a nuclear reaction, but we're not talking about that. So we use chemical equations as a shorthand way of describing chemical reactions. It makes it easier for us to see what's going on overall. They're somewhat like math equations, but instead of an equal sign, we use an arrow. And the arrow suggests the direction that this is going. The reactants are on the left, the products are on the right. So the reactants react to produce the products. And just like we read from left to right, we draw the equation from left to right. Oftentimes, the equations will include the physical states of the reactants and products. They will include the formulas. They'll give us the relative numbers of the different molecules that are reacting. And from that information, we can calculate, well, if I start with 5 kilograms of this, how many kilograms of product am I going to end up with? And those are very practical sorts of calculations. These are the, we call them state symbols. These are the abbreviations to indicate what state something is in a chemical equation. So G for gas, L for liquid, S for solid, and AQ means aqueous. It means it's dissolved in water, a water solution of that compound. So let's talk about the combustion of methane. And I don't have time for this story right now, but if you ask me during lab, I'll tell you the story of my 2 youngest children and the methane in the house. Methane burns to produce carbon dioxide gas and water. So here's the formula for methane. It reacts with oxygen. Here, oxygen is the element. Oxygen is a diatomic element, so when we see it present as an element, it's O2. It produces carbon dioxide and water. If we look real closely at this, we see that on the left side in the reactants there are 2 oxygen atoms, and on the right side there's 2 oxygen atoms in this molecule and 1 oxygen atom there. How could we start with 2 oxygen atoms and end up with 3? We can't. It means there's something wrong with our equation. There's also a problem with the hydrogens. In CH4 there are 4 hydrogen atoms. There's none in here. And then over here, there's no hydrogen in CO2, and the water has 2 hydrogen atoms. So here, this seems to suggest we're starting with 4 hydrogen atoms and ending up with 2. What happened? Did we change 2 hydrogen atoms into the oxygen atom? No, we did not. So this equation as written is going to violate the law of conservation of mass because you can't have atoms appearing and disappearing. So to fix that, we balance the equation. We adjust the equation. We're going to add coefficients. So we can change the number of oxygen molecules by putting a 2 in front of it. We can put a 2 in front of the formula for water. That means that we have 2 water molecules. You can't change the subscripts. You can't make it O4 to make it convenient because that's a different compound and that would change the chemical reaction. Okay? It would be a different chemical reaction. Here we have space-filling models representing the different molecules. And so if you use your imagination, you could imagine taking this molecule apart and taking these 2 apart and then putting them back together like Legos or Tinker Toys or something to make these new ones. Okay? Not super creative, right? But very simple. it is important that you understand that this is the idea behind all of the chemical equations. The number of carbon, hydrogen, and oxygen atoms that we start with is the same as the number of carbon, hydrogen, and oxygen atoms that we end up with. That is why the law of conservation of mass works, because all the pieces you started with are present when you end up. And so here we have one carbon, 4 hydrogens, 4 oxygens to start with, same number of each to end up with. Nothing happened to the atoms. They did not change into other elements or anything. They just got separated and repaired. Okay, it's a little bit like, I don't know, families or marriages or something, you know, people divorcing and remarrying, and there's all these different convolutions of families, right? I don't know. I'll just stop right there. Balancing chemical equations. So how do we know what kind of a coefficient to put and where? So this is a very loose set of instructions, a general approach. First, you need to start off with a skeletal equation with the formulas for the reactants and the products. The formulas need to be correct, okay? As you're writing these, some of them are just going to give you the names of compounds, and then you have to write the formulas, and that's good practice from the nomenclature stuff we just learned about. Before you go and balance it, though, look it up, check, and make sure that you've got the correct formula. Don't just Google the formula right away, because you're not ever going to learn how to write the formula. Give it your best shot, but then check your work before you go balance an equation with wrong formulas. Next, you start balancing. This is a method called balancing by inspection, which means we look at it and figure it out. Generally, this is a good idea to do atoms that are in more complex substances first, always doing things that are in compounds before we do any atoms that are pure elements. You take those elements, free elements, and do them last. The reason is when you're putting coefficients on compounds, compounds contain at least 2 elements. You're changing the number of atoms of each element. And so if you save one of those for the end, you might end up messing up another element that you already fixed. If you end with an element, then it's not going to mess anything up. It's possible to do balancing and end up with fractions. It's also possible to never end up with fractions if you don't like fractions. But if you do get fractions, you need to get rid of them by multiplying all the coefficients by the denominator of the fraction, because we need to have small whole numbers, lowest ratio, and then check that it's balanced. Let's do some examples. Here we're given sentences that describe chemical reactions, and we're going to get some practice. That's what we're going to get some practice writing formulas. Okay, so write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So the word "and" is like a plus. And that's not a very good one. Let's try that again. Let's make it fatter. So there's a plus, and this one down here, this and that, plus. To produce, that's where the arrow goes. So we've got silicon dioxide plus carbon reacts to form the arrow, silicon carbide, carbon monoxide gas. So we need formulas. Silicon dioxide is what kind of a compound? Molecular, acid, or ionic? It's molecular. If you find silicon on the periodic table, it's a semi-metal, right? But it's to the right of the line that divides the metals and the nonmetals. We don't have a separate nomenclature for compounds containing semi-metals. So kind of the rule of thumb is if the semi-metal is on the non-metal side, name it like a molecular compound. If it's on the metal side, name it like an ionic compound. So silicon dioxide. So silicon and dioxide means 2 oxygens, SiO2. What is the state of silicon dioxide in this reaction? Solid. They told us that. So we put S in parentheses. Plus solid carbon. Well, that's an element, carbon, and we put an S after that. You always have to ask yourself with elements, though, is it diatomic? No, it's not, so it's just C. And here we have the arrow. I'm leaving spaces here because I might need to write in coefficients. Silicon carbide. Well, that would be molecular, right? So Si, there's no prefix anywhere. Carbide would be carbon. You're like, What's the formula for silicon carbide?
The chemical formula for silicon carbide is SiC.
Siri's so funny. She pronounced it. It's sick. She likes it, I guess. It's SiC. So this is one where they left the mono off of the second element. They do that sometimes. I would not necessarily expect you to get this, but give it your best shot and then ask Siri, and she'll tell you it's sick. That's a solid. Carbon monoxide gas. What's the formula for that? CO. I wonder what she'd say to that. Should we ask her?
Yeah.
What's the formula for carbon monoxide?
The chemical formula for carbon monoxide is CO.
Boring. I was hoping she'd say CO or something. Okay, CO. So that's the first step, formulas. Now we need to balance this. So we do have an element. We want to leave carbon for the end. A lot of times it works out that if you just start on the left side and work your way across, it comes out okay. There's not one perfect way to do them, okay? It's sort of, an interpretation. And we should all end up with the same answer. Some places are easier to start from than others. Sometimes you may feel like you're starting to go around in circles. And if that happens, you end up just changing things and changing things. If that happens, check your formulas. If your formula is wrong, it may be impossible to balance. And if your formulas are correct and you're still having trouble, just start over and start with a different element. And that usually takes care of it. I'm just going to start at the beginning. Silicon, I have Si, there's 1 in this, and there's none here. So on the left side, I have a total of 1 silicon atom. And on the right side, how many silicon atoms do I have? 1. So that's already balanced. Then I'm going to move on to the oxygen. Here I've got O2. 2 oxygens on the left side. How many on the right side? Just 1. So if I put a 2 in front of CO, that will give me 2 oxygens. I can't change this into carbon dioxide. It needs to be carbon monoxide. So now my oxygens are fine. And when I did that, I didn't mess up the silicon. So now I'm going to look at the carbon. I have 1 carbon here, and over here I have 1 plus 2, 3 carbons. So how can I balance this? Put a 3 in front of the C on the left side. By saving that for last, when I change this and put a 3 on it, it's not going to mess anything else up. And so there's the balanced chemical equation. Some of them are very simple, and some of them will make you want to tear your hair out. Let's do another one. Write a balanced equation for the combustion of gaseous ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. There's a lot of gas going on there. Kind of like your uncle, yes. Or my sons on many occasions. Okay, so one of the reactants is C2H6. C2H6. And we're told it's a gas. What does that react with? Gaseous oxygen. So oxygen is in the gas state. Is oxygen diatomic? Yes, it is. So it needs to be O2. To produce, to form carbon dioxide, CO2, that's a gas, and water, and they're telling us that's a gas. When you write state symbols, sometimes it will give them to you. Other times it will want you to, the problem will expect that you figure out what it is. If it's giving you some information about temperature, then you need to take that into consideration. So here we have natural gas burning. Is this a hot environment or a cold environment or room temperature? It's going to be hot. Because why do we burn natural gas? To heat things up. Because we like fire, right? That's really the reason. Yeah, we're pyros. No, we do it mostly to heat things up. So at a high temperature, what's the state of water? It's a gas. At room temperature, it's a liquid. If it's really cold, like 20 degrees below zero, either temperature scale, then it's going to be a solid. On the periodic table, the colors of the elements on the one on the wall tell us what state they are at room temperature. So the ones that are blue, there's only two of them, mercury and bromine, those are liquids at room temperature. That's unusual. The ones that are black letters are all solids at room temperature, and the ones that are red are gases at room temperature. Ionic compounds are almost always going to be solid at room temperature. They have very high melting points. So those are the kind of predictable things. I would expect you to know that carbon dioxide and carbon monoxide are gases, just from general knowledge. Okay, so we've got that. I'm going to show you a different strategy. Some of you will like this, some of you will think it's stupid. Use it if you like it. If you don't, just shut up. So I'm going to draw a line separating the reactants from the products. So just a line dividing at the arrow. And what I want is for things to be balanced. It's a little bit like, balancing on a teeter-totter or something. We need the same amount of each thing on each side. And then I'm going to make a list, sort of take inventory. I've got carbon, I've got hydrogen, I've got oxygen. So I'm going to take inventory and see what do I have on each side. So in C2H6, I have 2 carbon atoms, I have 6 hydrogen atoms, and I have no oxygen atoms. In O2, I don't have any carbon, I don't have any hydrogen, but I have 2 oxygen atoms. In CO2, there's 1 carbon, no hydrogens, and 2 oxygens. I used to put zeros, but then they kind of looked like O's, so I'm just doing dashes. H2O, how many carbons? None. How many hydrogens? 2. How many oxygens? 1. Okay. We have inventory now. We need to compare on each side of the line. Carbon, a total of 2. And over here, a total of 1. So what I want to do is I want to multiply this so that I get 2. So I'll put a 2 in front of CO2. And then I'm going to fix the inventory. That changes this to a 2, and it changes this to a 4. So carbons are fine. 2 on the left, 2 on the right. Let's look at the hydrogens. 6 on the left, how many on the right? 2. How can I make that into 6? Multiply by 3. So if I put a coefficient of 3 in front of H2O, that changes the 2 to a 6, and it changes the 1 to a 3. Okay? Now let's look at the oxygen. On the left side I have 2. On the right side I have 7. What do I multiply 2 by to get 7?
You could do 3.5, but you can't really have
I could do 3.5, but there's no whole number I can do, right? So I'm just going to briefly show you the fraction method. People who get that will be fine with just a brief peek at it. If I multiply this by 7/2, then this would be 7, right? Now, this is balanced, but it's not proper. The correct balanced equation is balanced and the coefficients are whole numbers and they're the smallest ratio. So what I would need to do is I'd need to multiply everything by 2. I did 2 and 7 and 4 and 6. And that's clearing the fractions. Most students don't like to do that, so I'm going to show you a different way. Here we have 2, and here we have 7. It's like pairs of shoes, right? The oxygens come in pairs, and how can I get 7 shoes when I have to buy them in pairs? And I'm not allowed to throw one away. I call this the odd-even problem. So I've got an odd number here and an even number there, and I can't seem to reconcile it. Let's make them both even numbers. If I multiply an odd number by 2, it turns into an even number, right? So what I'm going to do is I am going to multiply everything I've already done by 2. So I'm going to put a 2 in front of this, and that changes the things below. So that's a 4, and this is a 12. I'm going to leave this guy alone because that's the one I was trying to fix. And then I'm going to change this 2 into a 4. So that changes this to a 4 and this to an 8. And I'm going to change this 3 into a 6. And I'm going to get 12 and 6. Are the carbons still balanced? 4 and 4. Are the hydrogens 12 and 12? Yes. So by doubling everything else, I didn't mess up the work that I've already done. But now I've got 2 oxygens here, and I want to get 14 on the right. And so I need to multiply by 7, and things will be beautiful. If I multiply by 7, then I've got 14 oxygens. There's my balanced chemical equation. To check it, go through and inspect it. 2 times 2 is 4 carbons. Here's 4 carbons. 2 times 6, 12 hydrogens. 6 times 2, 12 hydrogens. 7 times 2, 14 oxygens. Here I've got 8 oxygens plus 6 is 14. Any questions? Let's do one more. Balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. These are ionic compounds, aren't they? We've got lead and potassium in them, so metals, they're going to be ionic. So to write these ionic formulas, we need the formulas for the ions with their charges. Lead-2, what's the formula for that ion? Pb plus 2. Lead is Pb, and the Roman numeral 2 gives us the charge. It's not how many we have, it's the charge on the ion. What's the formula for nitrate ion? NO3, and what's the charge? Not 2 minus, just 1. Okay, so now that we have the charges, we know how to put them together. So Pb, NO3, 2. So we need 2 of those nitrates to balance the charge. The state symbol is AQ because we're told that it's aqueous. We're dealing with lead-2 nitrate that's dissolved in some water. And then we've got aqueous potassium chloride. Potassium is K. It's in group 1, so it has a +1 charge. Chlorine is Cl. It's in group 7. It's got a -1 charge. +1, -1. Just put them together. Also aqueous. And then we've got solid lead 2 chloride. Well, lead 2 is still Pb2+, and chloride is Cl-. What we're actually doing here, we'll learn about later, we're just swapping partners. So this becomes PbCl2, and that's a solid. We'll learn later how you can predict that that would be a solid, but for now we're just going based on what they said. And then we've got potassium nitrate, and so that's KNO3, and that's aqueous. I don't need parentheses for this 2 because chlorine is monatomic. I don't need parentheses on this nitrate because there's only one of them. Master in chemistry would consider it wrong if you put parentheses on it. And if you did that on something you're turning in handwritten, I would scribble it out for you.
Okay.
But yeah, you want to avoid that. So let's balance this one just by inspection without making an inventory. You can do the inventory. So looking at this, I have 1 lead, 1 Pb, and 1 Pb. So those are fine. Now this nitrate, I notice the title of this example, balancing chemical equations containing ionic compounds with polyatomic ions. Many times when polyatomic ions are involved, many but not all, the polyatomic ion stays together. So I have nitrate ions in the reactants, and I have nitrate ions in the products. The nitrate ion did not come apart. It's still NO3. So I can balance that as a unit. That can save a little bit of time and mental energy. So here I have 2 nitrate units. Over here, how many nitrate units? 1. So I can fix that by putting a 2 in front of the entire formula. Now I have 2 nitrates over there. You are welcome to balance the nitrogen and the oxygen separately. That always works. Potassium is next. I've got 1 potassium on the left side. How many potassiums on the right side? 2. So I need to put a 2 in front of KCl, so I've got 2 potassiums on the left side and 2 on the right side. And then how many Cl's do I have on the left side? 2. And how many on the right side? 2. It's not unusual for that last element to kind of take care of itself. And then double check. Go back through and make sure this one is correct. But you should go back through because sometimes when you fix one, you mess something else up, and you might not notice. Yes?
Because you want the lowest number.
Mm-hmm.
So if you just happen to, I don't know, miscalculate, you can just, take it off and subtract by 2, right?
That's a good question. So what if you end up with your coefficients here and it's not the lowest ratio? Then what you want to do is divide. You want to divide all of them by the common factor.
Okay. So
Yeah.
it would go into 6.
Yeah. So if you for instance went a little overboard and you had 3 is not a good example. 3 works. If I had 3 there and 6 here and 3 here and 6 here. That's not the lowest ratio, 3 to 6 to 3 to 6. I can divide all of these by 3 and get 1 to 2 to 1 to 2. There is a coefficient here, an understood coefficient of 1, but we don't write it because we're chemists and we avoid writing 1s.
But it would only work if they're both the same.
It would only work if, you would only need to do that if all of these numbers had one common factor that you could divide them by. Like if this was 5, then that's not a ratio that can be reduced. That would be the lowest ratio, and so there's nothing to do. And sometimes we end up with big numbers. You may find an example where you end up with, a coefficient of 25 or 36 or something. Don't be afraid of that. Some equations are like that. Any other questions?